Line spectra. When the vapors of some volatile substance are allowed to fall on the flame of a Bunsen burner and then analyzed with the help of a spectroscope, some specific colored lines appear on the photographic plate, which are different for different substances. For example, sodium or its salt emit yellow light, while potassium or its salts give out violet light. Absorption spectra. When white light is passed through the vapors of a substance and the transmitted light is then allowed to strike a prism, dark lines appear in the otherwise continuous spectrum. The dark lines indicate that the radiations corresponding to them were absorbed by the substance from the white light. This is called absorption spectra. Line spectrum of hydrogen. When electric discharge is passed through hydrogen gas enclosed in discharge tube under low pressure and the emitted light is analyzed by a spectroscope. The spectrum consists of large number of lines which are grouped into different series. The complete spectrum is known as hydrogen spectrum. On the basis of experimental observations, an expression was found: nu bar is equal to 109677 into 1 by n1 square minus 1 by n2 square per centimeter, where n1 is equal to 1, 2 and so on, and n2 is equal to n1 plus 1, n1 plus 2 and so on. The value 109677 per centimeter is called Rydberg constant for hydrogen. On the screen, atomic spectrum of hydrogen is shown. There are some series: Lyman, Balmer, Paschen, Brackett and P-Fund in the region. Lyman is in the region ultraviolet, Balmer in visible, Paschen, Brackett and P-Fund is in the infrared. So, equation known as Rydberg formula also can be written as 1 by lambda is equal to nu bar is equal to RH into 1 by n1 square minus 1 by n2 square. The relation is valid for hydrogen atom only. For other species, it is 1 by lambda is equal to nu bar is equal to R into Z square into 1 upon n1 square minus 1 upon n2 square. Z is atomic number of the species. RH is called Rydberg constant for hydrogen and n1 and n2 are integers. n2 is greater than n1. So for Lyman series, n1 is equal to 1. So n2 will be 2, 3, 4, 5 etc. And so for P-Fund series, if n1 is 5, then n2 is 6, 7, 8, 9. Thus by putting the values of n1 and n2 in the equation, wavelengths and wave number of different spectral lines can be calculated. Now Bohrs model of atom. Bohr proposed a new model of atom on the basis of Planck's quantum theory. The main points of this model are: in an atom, the electrons revolve around the nucleus in certain definite circular paths called orbits. Each orbit is associated with definite energy and therefore these are known as energy levels. These are numbered as 1, 2, 3, 4 or K, L, M, N and so on. Only those energy orbits are permitted for the electrons in which angular momentum of electron is whole number multiple of h upon 2 pi. Angular momentum of electron, that is MVR, is equal to nh upon 2 pi, where n is equal to 1, 2, 3, 4 etc. M is mass of electron. V is tangential velocity of revolving electron. R is radius, H Planck's constant. As long as electron is present in a particular orbit, it neither absorbs nor loses energy. Therefore, energy remains constant. When energy is supplied to an electron, it absorbs energy only in fixed amounts as quanta and jumps to higher energy states away from the nucleus as excited state. The excited state is unstable. The electron may jump back to the lower energy state, and in doing so, it emits the same amount of energy. That is, delta E is equal to E2 minus E1. Now, achievements of Bohr's theory. Bohr's theory has explained the stability of an atom. Bohr's theory has helped in calculating energy of electron. So, mathematical expression En is equal to minus 2 pi square m e raised to power 4 z square upon n square r square. And this value of En, it comes out minus 1312 into z square divided by n square kilojoule per mole. For hydrogen, Z is equal to 1. So En is equal to minus 1312 by n square kilojoule per mole. Limitations of Bohr's model. Number 1. The theory could not explain the atomic spectra of atoms containing more than one electron or multi-electron atoms. Bohr's theory failed to explain fine structure of spectral lines. Bohr's theory could not offer any satisfactory explanation of Zeeman effect and Stark effect. Bohr's theory failed to explain ability of atoms to form molecules formed by chemical bonds. It was not in accordance with Heisenberg's uncertainty principle. Now, de Broglie equation. De Broglie proposed that matter like radiation should also exhibit dual behavior, that is both particle-like, wave-like. De Broglie gave the relation lambda is equal to h upon mv. It means mv is equal to p. So lambda is equal to h upon p. Heisenberg's uncertainty principle. It states that it is impossible to determine simultaneously the exact position and exact momentum of an electron. Delta x into delta p is greater than equal to h upon 4 pi. Put value of p, then it becomes delta x into delta p is greater than equal to h upon 4 pi m, where delta x is uncertainty in position, delta px uncertainty in momentum, h is Planck's constant. Now, significance of uncertainty principle. Number 1. It rules out existence of definite paths or trajectories of electrons and other similar particles. Number 2. The effect of Heisenberg's uncertainty principle is significant only for macroscopic objects and is negligible for it is valid only for microscopic objects and it is negligible for macroscopic objects. Now, reasons for the failure of Bohr model. The wave character of electron is not considered. According to Bohr model, an orbit is clearly defined path. This path can completely be defined only if both position and velocity are known exactly at same time. And this is not possible according to Heisenberg's principle. Now, coming to important features of quantum mechanical model. The energy of electrons in atom is quantized. The existence of quantized electronic energy level is a direct result of wave-like properties of electrons. Both the exact position and exact velocity of an electron in an atom cannot be determined simultaneously. An atomic orbital has wave function psi. There are many orbitals in an atom. The probability of finding electron at a point within an atom is proportional to square of orbital wave function, psi square at that time.